So I continue. How many independent elastic constants? From this matrix, you can find three elastic constants: Young's modulus, shear modulus, and the Poisson ratio. I think during my study in the graduate program, I always have the examination like this. Please try to derive the relation between shear modulus and the Young's modulus and the Poisson ratio. We are asked to prove this equation. I'm not really asking you to prove this, but I will quickly go through the derivation of this relation and make you understand. You will have only two equations. No, you have only two independent elastic constants within your confined matrix. First of all, if you have uniaxial compression test, you will have sigma 3 equals to 0 and sigma 1 uniaxial compression test, correct? And you can plot a Mohr circle. Please remember, if you have normal stress at the direction 1, you will produce the normal strength at the direction 1, and you will produce the normal strength at the direction 3 as well. How much the epsilon 3 will be? The epsilon 3 will equals to the minus Poisson ratio times epsilon 1 because of Poisson's effect. Understand? So you will have another Mohr circle. This Mohr circle will be the Mohr circle of strain. So right now you have a Mohr circle of stress and you have a Mohr circle of strain. So I will start from this. The shear strain. The shear strain here divided by 2 will be the radius of the Mohr circle of strain tensor. Correct? This will be the radius. The radius of the Mohr circle will equals to the diameter of the Mohr circle derived from epsilon 1 and the epsilon 3 divided by 2. Correct? So epsilon 1 plus Poisson ratio times epsilon 1 will equal to the diameter. Divided by 2 will be the radius. So these two should be the same. And you can express the engineering shear strength as function of shear stress. So the shear strength will equals to shear stress divided by shear modulus. And the normal strength at direction 1 will equals to the sigma 1 divided by Young's modulus. Correct? And from the Mohr circle, for stress, you can understand the shear stress will equals to the sigma 1 divided by 2 because of sigma 1 will be the diameter of the Mohr circle and the shear stress will be the radius of the Mohr circle. So the shear stress will equals to the sigma 1 divided by 2. If you insert the shear stress into this equation, then you can delete the sigma 1 for two sides. Then you will have an equation like this, and you derive the relation between shear modulus and Young's modulus and the Poisson ratio. Okay? So how many independent elastic constants in your matrix? 2. If you know Young's modulus, Poisson ratio, you will know shear modulus. If you know shear modulus and the Poisson ratio, you will know Young's modulus. either two, you can derive the third one. So you have only two elastic constants within your compliance matrix. I can show you some other example. You will have the constraint modules. You will still remember the one-dimensional consolidation test. You will have the constraint module. It will be the same. The horizontal axis will be the axis 1 in the vertical direction, and the vertical direction axis will be the sigma 1. You could ask me, oh, professor, the slope should be Young's modulus. Why we say it is constraint modulus, but not Young's modulus? It will be the same, the relation between stress and strain in direction 1, correct? What is the difference between this and the previous one? What is the difference? The difference lies in the stress and the strain condition in the horizontal plane. For the previous condition, for Young's modulus, the horizontal stress equals to 0 because it is uniaxial compression test. So the lateral stress equals to 0. For the one-dimensional consolidation test, the horizontal strain equals to 0. The boundary condition is totally different. Do you understand? The previous one is uniaxial compression test. The horizontal stress equals to 0. But for this, the horizontal strain equals to 0. You will have the horizontal stress. For the previous case, the horizontal stress equals to 0, but you will have horizontal strain. The difference lies on that. So for this case, if the material is linear elastic, then you can express the constraint modulus as the function of Young's modulus. I already derived this equation here. I will not repeat it. So please derive this by yourself. I always like to ask a question about this when I teach this in soil mechanics. What do you think? M is larger or Young's modulus is larger? Which one will be steeper? Please raise your hand. If you think Young's modulus is larger than constraint modulus, please raise your hand. Young's modulus is larger than constraint modulus. Nobody? Good. It's because the constraint modulus is always larger than Young's modulus. So everybody has the correct answer. I know you are hesitating to write it. You can imagine it easily. If you have a sample, you did not give any stress at the horizontal plane, then I think it will be easier to deform the sample. If I put the constraint around the sample, they cannot move easily laterally. They cannot move laterally. Then it will become more steeper to compress it vertically. It will be more difficult to deform. Another thinking way, for this case, you will have a normal stress and you will have horizontal stress as well. Horizontal stress will produce negative strain at the vertical direction to compensate the displacement caused by sigma 1 because you have a lateral stress. So they will you have a lateral stress, you will become like this. So you will have a smaller vertical displacement. So that means you will have a steeper slope of this curve. It means the M will larger than E. The constraint modulus will larger than the Young's modulus. Anyway, I want to tell you, you will have several different kind of elastic constant, like constraint modulus. But constraint modulus can also be expressed as function of Young's modulus and Poisson ratio. So how many elastic constants you have? You still have only one. Only two independent elastic constants. I will try to introduce you another important elastic constant. We call it bulk modulus. You always heard about bulk modulus. If we apply a confining stress to a sample, to a rock, or to a soil, and you plot the relation between the volumetric strength and the confining stress. For linear elastic material, you will have a straight line again. And the slope, we call it the bulk modulus. And I derive the relation between bulk modulus and the Young's modulus and Poisson ratio. Like this, I will not repeat the derivation. You can have a look at that. It will be quite simple. Please look at that. Okay? Please derive it by yourself. I don't really have time to derive it by you, because you should already learn this from another lecture. I like to ask you to practice it again. You always need to practice something again and again, because it is very fundamental element. So you will find the bulk modulus can be expressed as function of Young's modulus. Okay? This will be a critical element. The volumetric strength will equal to epsilon 11 plus epsilon 22 plus epsilon 2. This will be a very essential relation. I think you already learned why. If you have a cubic like this, and if you have a string, and you have a linear stress at direction 1, direction 2, and direction 3. Then what is the volume change for this cubic? You can easily derive the relation between the volume change. The volume change will be, if the original cubic will be 1, 1, 1, then it will be 1. And this will be the 1 plus epsilon 1, 1 times 1 plus epsilon 2, 2 times 1 plus epsilon 3, 3. And if you expand this and delete the high order term, you will have this relation. Sorry, it should be 1 minus this. Okay? So the volumetric strength will equal to epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3. Actually, it will be the strain tensor, the invariant of strain tensor. I hope you still remember the invariant of stress tensor. You have I1, I2, and I3. And you will have invariant strain tensor. You will have I prime, I1 prime, I2 prime, and I3 prime. So this will be the invariant of strain I1 prime. Okay? So why I trying to focus on the independent elastic constant for isotropic material? I want to introduce you some different material for rock mass. We usually have a rock mass with 3 orthogonal joints like this. It will be frequently observed in the field like this. It's a little bit tilt, so it's tilt in this direction. Actually, it's still like a cubic, like a sugar, cubic sugar. We call it the orthotropic material, but not isotropic material. For rock mass, it's usually anisotropic. It will be extremely difficult to find a rock mass with the characteristics like isotropic material. Seldom. So you need to understand some material which is different from the isotropic material. So I will try to show you the linear elastic orthotropic materials. What is the elastic constant? You will find you have E11, E22, E33. The Young's modulus in this direction, the Young's modulus in this direction, and the Young's modulus in this direction. Nobody tell you the Young's modulus in different directions should be the same, unless you have isotropic material. Correct? And the Poisson's ratio will also differ. Mu 1, 2 means the Poisson ratio, which influences the normal strength at the direction 2 and the direction 3. Epsilon 2, 3 will be, when you apply a stress here, you will have a strength here and here. It will be Poisson effect, right? But the material could have a different response. If you apply a stress here, the expansion here and here could be different. So you will have a Poisson ratio 1, 2, 1, 3, and 2. Okay? And the shear modulus and the shear strength, you will have a G12, G13, and G23. It means the constitutive equation in this plane will be different from in this plane, will different from in this plane. So you will have a G12, G13, and G23. If the material is isotropic, then you will have a G12 equals to G13 equals to G23 equals to G. It will be isotropic materials. So for this kind of materials, you will have a, from here, you will have a 1, 2, 3. You will have a 9 elastic constant, but not really all of them are are how many independent elastic constant for isotropic material? A little bit forget about that. From here, you will have 9 elastic constant. 3 for Young's modulus, 3 for Poisson ratio, and 3 for shear modulus. I will check it. I will tell you. I will tell you tomorrow. Sometimes we will have the rock mass. We will have a rock mass like this. You will have a very clear sedimentary terrain, especially for sedimentary rocks. Can you recognize this? You have a sandstone shear embedded. So usually we call it transversely isotropic material. You will have a symmetrical plane in this direction. Can you imagine the plane which use this as the normal vector will be isotropic? You have a sedimentary plane like this. If you rotate in this direction, it will be anisotropic. But if you rotate in this direction, it will be isotropic. So you have a symmetrical plane horizontally. Okay, we call this kind of material transversely isotropic. I think maybe you are not the first time to hear transversely isotropic material. If you are the first time to hear this terminology, please write your name. For some students, it could be your first time to know this name. The transversely isotropic material is very important for rock. So you need to understand what is transversely isotropic. So here we will have the Young's modulus ES and EN. You will have 2 ES and 1 EN. What is N? N will be in the direction 3, which is the normal vector of the symmetrical plane. So for this case, the symmetrical plane is horizontal plane, and the normal vector is in the vertical direction. For this case, the Young's modulus in this direction and in this direction will be the same, because the horizontal plane is an isotropic plane. So we define S and T, and along S and along T it will be the same. So we have ES, and EN. So you can understand this, and this, right? How about the Poisson ratio? For Poisson ratio, you will have a 1 to 3. You will have a 1 to 2. You have a 1 to 3. Okay? You will have a 2 to 1. You will have a 2 to 3. You will have a 3 to 1 and a 3 to 2. Totally, you have a 6. Okay? In generally, 1 to 3 will be identical to the 3 to 1. The normal stress in direction 2 will influence the normal strength in direction 3. And the normal stress at the direction 3 will influence the normal strength in direction 2. The influence will be the same. So totally you have 6 different influence. 1 to 2, 1 to 3, 2 to 1, 2 to 3, 3 to 1, 3 to 2, 6. But actually you have only 2. You have only 2. 1 and 2. 1 and 3. And 2 and 3. Okay? So 1 and 3 should be the same with 2 to 3. Can you understand why? You can understand. But 1 to 2 will be different from 1 to 3 and 2 to 3. This, in this direction, will be different from in this direction. In this direction, will the same with this 2. 2 to 3 will be identical to 1 to 2. But 1 to 2 will be different. So you have 2 proton ratio. One proton ratio will proton ratio SD, and the other will be the proton ratio of NS. Can you understand? Okay. So you will have 2 Young's modules. You will have 2 proton ratio. How about shear modules? Shear modules, you will have a shear modules in 1, 2 plane, and shear modules in 1, 3 plane, and shear modules in 1, 2 plane. The shear modules in 1, 2 plane will be the same with the shear modules in 1, 3 plane. Will be different from the shear modules in 1, 2 plane. So totally you will have 2 Young's modules. One is GSD, and the other will be the GNS. You will have 2 GNS. Because of the shear modules in this plane will be the same with the shear modules in this plane. It will be the shear strength, shear modules NS, GNS. It will be the same. How many elastic constants you have? You will have 2 Young's modules, you will have 2 Poisson ratio, and you have 2 shear modules. So totally you have 6 elastic constant for the stress-strain relation for transversely isotropic material. But you have only 5 independent elastic constants for transversely isotropic. Why? Because on the symmetrical plane, the shear modules, Young's modules, and the Poisson ratio have a certain rule, have a certain relation, like I showed you. You have a symmetrical plane. The symmetrical plane will be isotropic. So the relation between Young's modules, shear modules, and the Poisson ratio at that plane can be clearly defined. They have a single relation. If you have a single relation, then you will reduce one independent elastic constant. So how many independent elastic constant you have? Originally you have 6, and right now you have a symmetrical plane. Then you have the relation between Young's modules, shear modules, and Poisson ratio. So you have only 5 independent elastic constant for an linear elastic transversely isotropic materials. I already tell you this. Okay, so you can read it by yourself. Okay. This will be, you already write this, right? No, I mean you already derived the elastic constant. No, you already derived the strength tensor for this case. For this homework, I like you to determine the principal stress and the principal directions for this one. And I give you the Young's modulus. If the material is isotropic materials, isotropic, linear, elastic, isotropic materials. I gave you elastic constant. I gave you strength. You have a strength, right? I give you strength. I give you elastic constant. Then you should you can calculate the stress state, which the stress increment, which produce this kind of strength. Okay. Then I wish you to calculate the principal stress and the principal directions. Since you have a principal stress and principal directions, you can evaluate the principal strength and the principal direction of strength. And you can compare the homework 7. The homework 7, you already calculate the principal strength and the principal strength directions from the measurement of this. You have, I give you this. Can you evaluate the strength tensor? Yes, right? If you have the strength tensor, you can calculate the stress tensor increment, right? Using the stress-strain relation. Then you will have a stress tensor. Since you have a stress tensor, you can evaluate the principal stress and principal stress direction. Please compare with homework 7. You derive the principal strength and the principal strain direction. Please compare if the principal stress and the principal strain is in the same direction. Of course, they should be in the same direction. Okay? If I ask you to write this, I think it would be easier for you if I turn the homework back to you. Then you can compare it, right? So I will try my best to turn your homework back to you at the next Thursday. And please give me the homework at Friday. Please write your homework beforehand, and I will turn out your homework at the Thursday so you can compare the results. Okay? Here,